So we know how to create a model, how to create a simple regression model, linear regression model. We know how to compute regression coefficients that will give us the best fit. So the sum of squared errors, the distances between the predicted and the real y values, will be as small as possible. Okay. Now let's discuss how to evaluate the model. And when we talk about evaluation, we actually need to take into account two things. First of all, before you actually create a model, you need to find out how good the relationship between x and y is. And that's what we've been doing last time, right? So, the last lecture. So we need to make a scatter plot to see if indeed we have a linear trend. Then we can calculate the coefficient of a correlation that will tell us how strong the trend is. After that, we create a model and evaluate how good your model is, including look at the predicted relationship between predicted and real y values, calculate different statistics that will tell us, that will allow us to evaluate, to assess the quality of your model. So let's discuss that. The evaluation of linear relationship we already know something about it, as well as about the correlation coefficient. I'll just repeat it quickly to introduce the case. Well, the case is actually the same I've shown you before. We're trying to find out if there is any relationship between age of a person and the annual income. And of course, we are talking about our people data. We are not talking about people that are living right now. Okay. So if you make a scatter plot, you can see that the points are aligned quite close to a straight line. Of course, they are scattered, but we can see a very clear linear trend. And if you calculate the correlation coefficient, it will get 0.88, which is strong correlation. Okay. So it means that we can try to make a simple linear regression model that will predict the income of a person by age. So that's the model. Okay. So the model tells us that if you want to predict income by age for this particular sample at least, you need to take age, x, multiply to 830 and subtract 1156. Which means that if a person gets older by 1 year, the salary of this person will increase in average, of course, because it depends also on many other things, will increase by 830 euro. Okay. Now let's try to calculate, to use this model for making some calculations. Okay. I take the first record, this one, and then you can see that the age of this person is 48 years. Okay, so this is 48 years. I'll multiply it to the slope, and then subtract the intercept. So if I do all the calculations, that's the value I've got. So that's the predicted value. And I made a column with predicted value, so you can see it here. And you also can see that this is the real value, 45,000. So the predicted value is smaller by 7,000, approximately 7,000 than the predicted value. Okay. And then you can repeat this for every record and get the predicted values. These are the predicted values. Okay. And how the predicted values will look on the plot? Well, it's very simple. All predicted values align on a straight line because it's a part of this line, right? These points are part of this line. So you can see, for example, if you take this person, this is the real value, this is the predicted value, and this is the error. This is the error of prediction. Okay. Now look, we always can get the vector with predicted values, regardless which the model to be used, right? Simple model, multivariate model, nonlinear regression. We always have the real y values and the y values that model predicts. Okay. That means that we can investigate the relationship between the predicted and real y values in order to find out how good the predictions are, how good the model is. And first of all, we can make a scatter plot. So we have predicted versus measured values. That's how it looks like for our case. So instead of the data, now I see this is the real y values. This is these y values, these ones. Okay. So I took all these values and used them as x in this case. And then these are the predicted values. So this is what model predicts. So these are all these values. Okay. Now let's think a little how this value should look like. Okay. So let's take the first one, the Lars. Okay, Lars has the salary 45,000, but the predicted value is 38,000. So you can see that this is the real salary, and this is the predicted salary. And of course, it's under predicted. The real salary is 40. The good prediction will be like this, right? So this is 45,000, right? So that's where the point should look like. Okay. Then if you make a line fit for all these points, in ideal case, the line should have a 45 degrees. No intercept, of course, and the points should lie exactly on a straight line. But you will never get this. You will never get this. Okay. So visually, you can see that the model is not very good. So we have some big spread around between the predicted values and the real values. But how to estimate this spread statistically? So let's learn a couple of new statistics that will allow us to see how good your model is, how good the predictions are. Let's start with coefficient of determination. It's one of the widely used, most used statistics for regression models. Well, let's look at this one. So this is the coefficient of determination. It tells the following: take the sum of squared errors and divide to the sum of the squared distances between y values and the average, and then subtract it from 1. Let's try to find out what's the meaning of this. Okay, let's take one particular point. So look, this is the average value. This is the distance between the average value and the y value, and this is the error. So this is the distance between the predicted and the real values, right? Now, what if we compute the following? We take every distances like this for every point, square it, and then take a sum. You remember what? That's the variance. If we divide it to n minus 1, if we take SS dot, sum of all these distances, and divide to n minus 1, we will get a variance for y, right? S, of course, variance for y squared, right? So that's a variance for y. So sum of squared distances between the average value and the real y values gives us almost a variance for y. We just need to average it, right? Now let's take another sum. Let's take these distances, the errors, and also square them, because we are interested only in absolute values, and take a sum. So it means that we can also calculate the variance for errors, right? So it's a sum of these squared errors divided to n minus 1. Okay. So what in fact this ratio does? This ratio tells us how big the error variation, if we take into account the total y variation, how big the part of y which we cannot predict precisely. Okay. For example, imagine that the error variation, the ratio between these two variances, let's say 0.3. It means that 30% of variation of y values, of the variance of the y values, cannot be explained by the model. Because model is not good enough. Okay. What if you take 1 minus this? Well, that's what we explain. If this is what we cannot explain, this is what we explain. So 70%, in this case, 70% of the variation of y can be predicted by the model. So it means that 70% of the y variance can be explained by the x variance. So x has a certain relation to y. Okay, so that's the coefficient of determination. It tells you how much of y variance can be explained by x variance, or can be explained by model. And if we calculate the coefficient of determination in our case, we will get 0.783. What it means? Well, it means a simple thing. It means that 78% or 78.3% of income variation or variance can be explained by the age. Or, of course, age-related factors, because we have a lot of factors related to the ages, like experience and so on. Okay, so 78%, it's quite a lot. But still we have 22% unexplained, because salary income depends on many other things also in our sample.